Hello everyone, welcome back to the channel. In the previous videos, I had explained the series and parallel circuits. In addition to that, I had solved some numericals for series as well as parallel circuits. In this video, I will talk about resonance in both series and parallel circuit. So video will be about the basic concepts of resonance and the different behavior of the circuits under series and parallel conditions. And I will solve the problems of the resonance in the next video. So the resonance is it's an important condition in case of electrical applications as well as in the field of telecommunication. We can say a circuit is in resonance when the voltage across a circuit is in same phase with the current through the circuit. So when voltage and current they are in same phase, it means power factor is unity. So that is the basic condition for resonance irrespective of whether it's a series circuit or it's a parallel circuit. So we can say the impedance is purely resistive, only then the power factor is unity, or the reactance of the circuit is 0. So this is what we can say, impedance is purely resistive and net reactance of the circuit is 0. Now the series circuit will have some different behavior and parallel circuits behave in different way under these conditions. So let's start with the series resonance. For series resonance, let's say we have R, L and C, they are connected in series across a voltage source. Current through the circuit is I. Now current is dependent upon the impedance, and impedance is given as R plus J XL minus XC. Now the main condition is that impedance is purely resistive and net reactance is 0. So from here what we get, that this XL minus XC, it should be equal to 0, which gives XL is equals to XC. So XL is 2 pi FL, XC is 1 upon 2 pi FC. Since this is resonant condition, we can denote the frequency either by F naught or by Fr, which is known as resonant frequency. Now this condition comes only for a particular frequency, since both XL and XC they are dependent upon frequency. So let's say we denote it by F naught, then F naught becomes 1 upon 2 pi root LC, or we can say omega naught, that is the angular frequency at resonance is 1 by root LC. Since XL minus XC is 0, so Z is equal to R only. Now if you want to check that what is the power factor is cos phi, which can be calculated as R by Z from the impedance triangle. Since Z is equal to R, so R by R it's 1, which is satisfied. This is the actually main condition. Now at resonance, if we want to calculate the current, which is V upon Z, it will be equal to V upon R. So it's I naught, since this is corresponding to the resonant frequency. Since Z has minimum value, which is equal to R, so current I naught is actually maximum current. So current in the circuit is maximum at resonance in comparison to all other frequencies. Similarly, at resonance we can find out the voltage across inductor or capacitor. So let's denote the voltage across inductor as VL naught, which will be same as VC naught. Now why they are same? Because VL naught is equal to I naught XL naught. VC naught is equal to I naught and XC naught. And what we had seen that at resonance XL and XC both are equal. That's why VL and VC both are same at resonance. Also, this I naught is maximum. That's why the voltage across the inductor or voltage across the capacitor is also maximum. In fact, this is many times in comparison to the supply voltage. We say that in case of series circuit, voltage magnification takes place. We have voltage magnification. Series resonance is also known as voltage resonance. Now, if you want to draw the phasor diagram, now in case of series circuit, current is common through all the circuit elements, so it's taken as reference. Voltage across the resistor is in same phase. Voltage across the capacitor that lags behind the current by 90 degree. Voltage across the inductor leads the voltage by 90 degree. Since they are equal in magnitude, so they will cancel out each other and voltage VR, which is equal to V, is in same phase with current I. And that's what we have. We can say the power factor is unity. Now, if you want to see the behavior of this resistance, inductance, or capacitance with respect to frequency, we can plot that also. RLC, then we can say impedance, current, everything. On this x-axis we have frequency, on y-axis reactance, impedance, resistance, current. Now resistance is constant. Then we have XL, which is equal to 2 pi FL. So XL will increase linearly. XL. Then we have XC, which is 1 upon 2 pi FC. Now since this capacitive reactance has opposite nature to to inductive reactance, so it will be represented in the fourth quadrant. So this is a variation of XC. Now XL minus XC, that is the resultant XL minus XC, is like this. So at this point, when XL minus XC is 0, that is actually corresponding to the resonant frequency F naught. So at that time, impedance is equal to resistance only. So the impedance is like this. This is how the impedance varies. Its minimum at resonant frequency. It keeps on increasing if we go on decreasing the frequency below the resonant frequency. And in fact, if we increase the frequency beyond the resonant frequency, it will start increasing. Now what this happens, because Z is equal to r square plus xl minus xc square under root. At resonance, xl minus xc 0 z is equal to r corresponding to this. Below resonant frequency, xc is more in comparison to xl. So if we go on decreasing the frequency, xc, if we decrease the frequency, xc will increase and xl will decrease. So this gap between xl and xc that keeps on increasing. That's why the impedance is increasing with decreasing frequency. Similarly, if we increase the frequency, xl will start increasing and xc will start decreasing. Again, the gap between xl and xc that keeps on increasing, which leads to increase in impedance. The impedance is increasing from this point till this one, or it keeps on increasing depending upon that how we are increasing the frequency. So current which is inversely proportional to impedance, that will have the shape like this. It's maximum at resonance and it will have some low value over here and over here. So again it is controlled by the variation of frequency. Now what we can see over here, that below the resonant frequency, capacitive reactance is more, so circuit is having capacitive nature, so power factor is leading. And the frequencies which are more than resonant frequency, XL is more in comparison to XC, so the nature of circuit is inductive and power factor is lagging power factor. And at resonant frequency, power factor is unity. Now let's plot the variation of current only. With frequency. Now it can be frequency f or angular frequency. The current varies like this. This one is the maximum value I naught, which is V upon R, which is corresponding to frequency omega naught or f naught. Now why we need this graph? In order to find out the bandwidth. Now in case of RLC series circuit, this bandwidth is defined as range of frequencies for which the power delivered to the circuit or to the resistance is greater than or equal to P naught by 2. P naught by 2, where this P naught is actually power delivered at resonance. So we can say these are the two frequencies. This one is denoted by omega 1, denoted by omega 2. Since the power delivered is half, at resonance, P naught is equal to I naught square into R. Half power, we can say half power, since it's P naught by R, half power is P naught by 2, sorry, not R, it's P naught by 2, I naught square by R into R by 2. We can write it as I naught by root 2 square into R. So this one, corresponding to this, the current value is I naught by root 2. So I naught, the current at resonance, and this one is I naught by root 2. So these two frequencies, f1 and f2, or omega 1 and omega 2, they are known as half power frequencies, also known as lower cutoff frequency and omega 2 or F2 is known as upper cutoff frequency. Now you can derive their expression omega 1 and omega 2 by, let's say, at omega 1 current is I1, which is equal to I naught by root 2. At omega 2 current is I2, which is equal to I naught by root 2. You can calculate the power in terms of current. I1 will, or I2, they will have value V upon Z, V upon R square plus XL minus XC square under root V upon root R square plus omega L minus omega C square. Since you have some value of frequency over here, you can equate this to I naught by root 2, where I naught is V by R. So when you solve this equation and find out the two values of frequency, then omega 1 comes out to be omega naught minus R by 2L. You can find out these derivations in any of the book. Omega 2 as omega naught plus R by 2L. And the bandwidth is actually range of the frequencies where power delivered to the resistance is either half of the power at resonance or more than that. So its bandwidth is omega 2 minus omega 1, which is given as R by L. And if we have to write these in terms of frequencies F1, F2, then F1 is F naught minus R by 4 pi L and F2 is F naught plus R by 4 pi L, and bandwidth, which is F2 minus F1, that will be equal to R by 2 pi L. Next is the quality factor. Now in case of series circuits, voltage magnification takes place and the quality factor is measure of that voltage magnification. It is defined as the ratio of voltage across the inductor or across the capacitor to voltage at resonance. Voltage across inductor or capacitor, either of them, upon voltage at resonance. So voltage across the inductor is I naught XL naught, and voltage across at resonance is B, which is equal to I into R. So it's XL naught upon R omega naught L by R. Similarly, if we want to write it in terms of voltage across the capacitor, I naught into XC naught IR, so XC naught upon R 1 upon omega naught RC. So if you use the value of omega naught either in this expression or in this expression, Q is, let's say I'm using the upper one, omega naught L by R, It's 1 by root LC into L by R. This expression becomes 1 by R root L by C. Same expression can be driven from here if we use a value of omega naught as 1 by LC. Now coming to the parallel resonance, the condition for resonance that remains same, that power factor should be unity. Now in order to understand the parallel resonance, let's take the example of a practical parallel circuit where we have a RL branch, series combination of resistance and inductance, or we can say we have a coil which is connected in parallel with a capacitor of value C, and these are connected across a voltage source having value V. Current through the circuit is I, and then we have this branch having current I1 and this one is having value I2. XL is the inductive reactance and XC is the capacitive reactance. Now we can have different parallel circuit as well. Now if we want to find out the admittance of this parallel circuit, the main motive is that voltage and current, they should be in same phase. For finding out that the condition that when will these two will be in same phase, we need to find out the admittance, and the imaginary part of the admittance, or we can say the susceptance of the circuit, should be 0. For finding out admittance Y1, it will be equal to 1 upon Z1. Z1 is R plus J XL. So we have to rationalize this, and we can write this one as R minus J XL upon R square plus XL square. This is what we had already done in case of parallel circuits. If you haven't seen that, you can check the video in the description box. Similarly, Y2 is 1 upon Z2. Z2 is minus JXC. It can be written as J upon XC. Now the net admittance Y, that will be equal to Y1 plus Y2. Now how we come across this? 1 upon Z1 is equal to 1 upon Z1 plus 1 upon Z2. 1 upon Z is Y, 1 upon Z1 is Y1, 1 upon Z2 is Y2. Let's use the value of Y1, R minus J XL upon R square plus XL square. Z Y2 is J upon XC. Separate the real part, which will represent the conductance, R upon R square plus XL square. The imaginary part, 1 by XC minus XL upon R square plus XL square. Since at the resonance, the susceptance should be 0, so 1 upon XC minus XL upon R square plus XL square, it should be equal to 0. This one represents the conductance, only this is present in the circuit, and not like present, we can say this is actually affecting the amount of current at resonance, and the phase angle is controlled by this one, and that's why they are in same phase. These two, 1 upon XC and XL minus XL upon R square plus XL square, their net value should be 0. So from here what we get, 1 upon XC is equal to XL upon R square plus XL square. XL into XC, it should be equal to R square plus XL square. Now at resonance, XL is equal to omega naught L Xc is equal to 1 upon omega naught c. So omega naught L to 1 upon omega naught c is equal to r square plus xl square. L by c equal to r square plus omega naught square L square. So from here we will get the value of omega naught, that is the resonant frequency in case of parallel circuit. It will come out as 1 by root 1 by LC minus R square upon L square, and if we want to write F naught, it will be 1 upon 2 pi root 1 by LC minus R square L square. And the if the resistance is very small in comparison to the inductance, then F naught becomes 1 upon 2 pi root LC, same as in case of series resonance, and omega naught is 1 by root LC. Again, same as in case of series resonance. And in fact, the expression for resonant frequency in case of parallel circuits depends upon that how many number of elements are connected in one branch, whether we are having only resistive only, capacitive or only inductive branch, or we have the circuit like this which we had used over here, or we can have the combination of resistance and capacitance in the second branch. So accordingly the expression for the resonant frequency will change, but the basic concept will remain same, that is for resonance the power factor should be unity. Now let's find out that what's the value of impedance at resonance in case of parallel circuit. Now impedance, which is equal to 1 upon y, since this part is 0, so it will be equal to y is equal to r upon r square plus xl square. So z becomes r square plus xl square upon r. Also what we had seen that at resonance r square plus xl square is equal to xl into xc, which is equal to L by C. So let's use that value over here. So y is equal to r upon L by C. Sorry, not. And z becomes L by RC. So this L by RC, it will not have the units of impedance, but it represents the impedance. That's why it is known as dynamic impedance. It's dynamic impedance of the parallel circuit. Now if we have to find out the current at resonance I naught, it will be equal to V upon this dynamic impedance, V upon L by RC, or V RC by L. So current at resonance is actually minimum in case of parallel circuit. And if we have to draw the phasor diagram, in case of parallel circuits, voltage is considered as reference. The current through the capacitor that will lead the voltage by 90 degree, and then we have an RL branch. So for RL series branch, the current lags behind the voltage by some angle which is between 0 and 90 degree. Let's say that angle is phi. This is IL. So this IL will have two components, IL cos phi and IL sin phi. So IL cos phi is in same phase with the voltage, which represents the resonant condition. It means IL sin phi and IC, they cancel out each other. IC is equal to IL sin phi and I is equal to IL cos phi, which is in same phase with the voltage. Now, if we have to show the variation of the susceptance or the conductance, that can also be shown with respect to the frequency. We can say we write impedance or admittance. For that, let's consider the resistance is 0. So when the resistance is 0, then the inductive susceptance is 1 upon j xl, which can be written as minus j by xl minus j upon 2 pi fl. Capacitive susceptance 1 upon minus j xc, j upon xc or j 2 pi fc. So how will these two vary? Since we have considered the resistance as 0, so that will not be represented over here. We can represent y and b frequency. The capacitive susceptance, that is directly proportional to frequency. So it varies linearly. BC. VL is inversely proportional to frequency. Minus sign over here. It has opposite nature. So it is represented in the fourth quadrant BL. And the resultant BL minus BC is, or BC minus BL, and this one is corresponding to the resonant frequency. So all the frequencies less than f naught, BL is more, so it means circuit is having inductive nature. So lagging power factor is there. Power factor is lagging below the resonant frequency. And when frequency is more than resonant frequency, capacitance is more dominating and the circuit nature is capacitive, hence the power factor is leading power factor. And at resonance, the power factor is unity. Now, in case of parallel resonance, we can have the quality factor, which will give us the measurement of current magnification. Since in case of parallel circuits, there is magnification of current. Though these two currents are cancelling out each other, but the current through the inductor or current through the capacitor, they are many times in comparison to the total current. So quality factor is calculated in case of parallel circuits as current through inductor or capacitor upon current at resonance. So current through the inductor or capacitor, let's say we write the current through the capacitor as IC naught, current at resonance I naught. IC naught will have value V upon XC naught. V into XC is 1 upon omega C, 1 upon omega naught C. I naught is equal to V upon ZD, that is the dynamic impedance. So V upon L by RC or V RC V upon L. So let's substitute these values over here. Then the quality factor is omega naught C upon omega naught CV upon R CV by L, which gives us the expression as omega naught L by R, which is same as in case of series resonance. And if we use omega naught as 1 by root LC, then quality factor becomes 1 by R root LC. We will get the value of quality factor same even if we write it as IL naught by I naught. You will get the same expression of quality factor. In the next video, I will take the numerical problems based on the series and parallel resonance. Thanks for watching the video.